So when you do these instantaneous center problems, they fall into three categories. In category one, you're given the velocity and omega, the angular velocity, and you can figure out the instantaneous center from that. In category number two, you're given the velocity of two different points, and these velocities are not parallel. I would say this is the most common type of problem. And the third type is where you're given two velocities at two different points, and they're parallel, and that's a special case. So here is the first example we're going to do. And in this case, you notice that you're given the velocity of center, so the velocity of a certain point at 4 feet per second. And you're given the angular velocity omega at 6 radians per second. So this falls into that first category. They also give you the information that the belt, not the disk, is moving at 12 feet per second to the right. And they say that it may or may not be slipping. And that's for us to determine. So in that case, don't be misled. That velocity, 12 feet per second, at the bottom there is probably not the velocity at A, unless we're very lucky. So the problem is asking us to find the instantaneous center, find the velocity at A and B, and they want us to determine if it's slipping. And if I had to guess, it probably is. It would have to be a very special combination for it to not be slipping. Okay, so this is a type 1 problem where you're given the velocity and the omega. And so we know that the velocity is r times omega. So we're given the velocity is 4. We're given the angular velocity omega is 6 radians per second. And so the radius from the instantaneous center to point C, which we're given the velocity for, is just going to be 4 divided by 6, and 4 feet per second divided by 6 radians per second, and that comes out to 2/3 feet. Okay, so we need to then locate where this 2/3 feet is. So here's point C, and perpendicular to that velocity, the instantaneous center is going to be 2/3 of a foot away. So it could be either here, 2/3 of a foot down, or up 2/3 of a foot. But we're given that the omega, the angular velocity, is counterclockwise at 6 radians per second. So you can see that if it's rotating counterclockwise, the top point can't be correct. Because if you are spinning counterclockwise around this top point, C would be moving to the right, but it's moving to the left. So this is incorrect. This is the correct location down here for the instantaneous velocity. So what that means is that the instantaneous center is 2/3 of a foot below the center. Okay, so to get the velocity of point B, which is at the top of the circle, we need to get the distance from the instantaneous center to that. It's a 1 foot radius, and it's 2/3 of a foot below the center, so it's 1 2/3 foot to point B. We'll also need the distance to point A, which will be 1/3 of a foot. Okay, so the velocity is just omega times the distance from the instantaneous center. So we're given that omega was 6 radians per second. And so the distance from the IC to point B is 1 2/3 foot, or 5/3 feet. So 6 times 5/3 is 10 feet per second. The distance to point A is just 1/3 of a foot, so 6 times 1/3 is 2 feet per second. The last thing is to determine the directions. So remember, we're spinning counterclockwise around the instantaneous center. So if this is the pivot point, the instantaneous center. So if you're spinning counterclockwise about that, this top point is moving to the left, and the bottom point is moving to the right, and that's how we get these directions here. Now notice the disk is moving at 2 feet per second to the right. The belt is moving at 12 feet per second to the right. They're not the same speed, so the belt must be slipping. If they weren't slipping, they would have the same velocity. So it's slipping. Okay, so here's an example where it's rolling without slipping. Okay, if the problem specifically says the disc or the wheel or the ball is rolling without slipping, that means it's rolling without slipping. or if it's obvious, like a disc like this one unrolling from the string like a yo-yo, it is not slipping. And so if it's not slipping, the point where the ground or the string is touching the disc is not moving, the string is not moving, the ground's not moving, therefore the velocity is zero because there's not slipping. They have the same velocity, which means that the point of contact is the instantaneous center of velocity. So right here where the string touches the wheel is the IC. Okay, we're given that omega is 2 radians per second counterclockwise. So the velocities are just going to be r times omega. So we need to get the distance from A to B. So this distance here we can figure out is 7 inches times 2. 14 inches per second, and since we're rotating counterclockwise around the instantaneous center, that's going down. Point A, we need to figure this distance, a little trickier, not that bad. We'll use Pythagorean's theorem. This is 5 inches, that's 2 inches, so square root of 2 squared plus 5 squared is the radius from the instantaneous center to point A. And omega was 2 radians per second, so that turns out to be 10 inches per second. And again, it's perpendicular to the radius from the instantaneous center to the point. And so the direction of velocity A is down and to the right. And if you do the angles, it's 2 to 5. If you look at that triangle, it's 2 to 5, and you can figure out that theta, arctangent of 2 over 5, is 21.8 degrees. Now, this is probably the most common type of problem you'll have. Find omega of AB. So we know that this is the instantaneous center for AB. And so to get omega of AB, we need to know the velocity of B, which we don't know. If we could get the velocity of B, we would divide it by 5 inches, the distance from A to B, and that would give us omega. What we do know is the velocity of C. So somehow, knowing the velocity of C, we're going to have to get the velocity of B. And so that implies maybe doing an instantaneous center problem. And so here you have the velocity of C going 12 inches per second that way. And here you have the velocity of B going, let me try and draw that a little better. The velocity of B going perpendicular to the arm AB. Okay? Probably it's going this way. And so remember, the instantaneous center, the velocity is perpendicular from the distance to the instantaneous center. So we know perpendicular to that velocity, which will be right along the arm, because the velocity is perpendicular to the arm, so the arm is perpendicular to the velocity. And perpendicular to this velocity, that's the R. So where these two perpendicular lines meet, that must be the instantaneous center. So there we go. The instantaneous center is somewhere over there. And so I've redrawn that triangle down here. Okay, so I'm calling the distance from the instantaneous center, which I've labeled O, to point C, RC, and I've called the distance from the instantaneous center to point B, RB. So we know this angle here is 45 degrees, alternate interior angles. We know this angle is 30 degrees, and 30 plus 45 is 75, minus 180. We know that this angle ends up being 105 degrees. And so then we need to figure out RC and RB. Just going to use a law of sines. So we got 4 inches divided by sine of 45 degrees will equal RC divided by the sine of 105 degrees. And so that gives RC is 5.46 inches. And similarly, RB over the sine of 30 degrees, the opposite angle, will be equal to 4 inches over sine 45, and that gives RB is 2.83 inches. Okay, so now that we know the distances, okay, we would remember the velocity is the distance from the IC times omega. Okay, so let me draw that again. So here's the IC, we know it's 5.464 inches to point C, and we were given that the velocity of C, I think, was it was 12 inches per second going up. Let me double check that. 12 inches per second going up. So, it looks like I made a mistake. I put 6 inches per second. It's 12 inches per second. Oh, so that should be 12 inches per second. Unless I just wrote it down wrong. But let's solve it for 12 inches per second. So 12 inches per second divided by 5.464. I get 2.196. I'm off by a factor of 2 radians per second. And then we know that the velocity of B is going to be this omega, which is now 2.196, times this distance, which we calculated just now as 2.828 inches. And so I have, this is 2.196. And that makes this, I'm off by a factor of 2 on everything, 6.211 inches per second going up. And then so finally we know that point B is spinning around A, because this was given as a pivot point, and B is going at 6.211 inches per second, and we were given that this distance was 5 inches, so that divided by 5, and again everything off by a factor of 2, 1.242 radians per second.